Hi everyone, this is Drew Wharton with Nimble Leader, along with my colleague Scott McMartin. Scott is Managing Director with Nimble Leader. He's also Vice President of OnTime Edge. Scott aligns manufacturing execution strategies with the symptoms and root causes of current manufacturing throughput and profit performance. Scott, before we begin, do you have anything to add?
Thanks, Drew, for the introduction. Hello, everyone. For most of my career, my focus has been to assist manufacturers to establish and sustain a market leadership position through accelerated material flow. Today, as we introduce you to the power of balanced manufacturing flow, I hope the concepts we discuss are as thought-provoking for you as they have been for me, and may they inspire you to take action to improve your own operations.
Thanks, Scott. During our time today, we're going to review and discuss three concepts related to balanced manufacturing flow. First, we're going to touch on TOC, Theory of Constraints, a transformative approach enabling significant operational and profit improvement over time. Second, we'll address drum buffer rope, the engine to high on-time delivery. And third, we're going to cover key throughput measures, the high-octane fuel to manufacturing value creation. Okay, let's step into our session today on the power of balanced manufacturing flow. Scott, you've often said that theory of constraints within the context of balanced manufacturing flow is a game changer. At the start of our session today, why is this the case?
Drew, TOC really should be thought of as an integral part of any continuous improvement framework, not as a standalone or competitive model. Theory of constraints, or TOC, provides the means to improve system throughput by focusing on maximizing the throughput of the system's constraint. Here we see the typical improvement enabled in companies that have embraced TOC over the past 30 years, starting with 25% more throughput, more stuff out the door. Next, an improvement in capacity and asset utilization to the tune of about 30%. So not only are we getting more stuff out the door, the right stuff out the door. 50% less operating expense and inventory. Operating expenses like overtime and expedited freight, penalty fees, outsourced operations. 60% less order cycle time. And the big one here, 98+% of on-time delivery. Some companies over the past 30 years that have been really exemplary in their application of theory of constraints have been companies like Amazon, Medtronic, Softmore Danek, and Ashley Furniture.
These are really impressive results related to optimizing against the system constraint. So thanks so much for the overview. Now, Scott, you have talked about bottlenecks. How do they relate to the theory of constraints methodology?
All systems have constraints. That being said, eliminating constraints is not realistic, nor is it as important as identifying and managing the constraints. Here's a simplistic representation of the physics of flow. All systems are limited by their constraints, which could be physical resources such as machines, skilled labor, or even space, material availability, or even market demand. In the short term, it is important to recognize constraints exist and learn how to proactively manage them. Longer term, the focus is to elevate the constraint for more capacity to do more business.
Okay, so focusing on and elevating the constraint in the system is key when making decisions about manufacturing flow. Now, Scott, you say that there are 5 focusing steps to theory of constraints. Can you share with the group what you mean here?
Yes. So first of all, we need to identify the constraint. If every system has a constraint, then let's find out where it is. And it may not always be where you think. It could be a machine. It could be a skilled resource, people. It could be material availability, which has been a big one over the last couple of years. It could also be something as esoteric as a policy or a closely held belief of the management of the company. So whatever it is, the first step is to identify it and understand why it is what it is, where it is. Next step would be to exploit the constraint. So now that we know where it is and that it is dictating the overall throughput of our organization, what we want to do is make sure that it's only working on product that we have sold to customers. We don't want to be working on product that ultimately ends up going into a warehouse. Also, we only want to work on good parts. We want to make sure that the quality of the material going into the production process is at the level it needs to be. Third, we want to subordinate everything to the constraint. So that means that we don't want to overactivate all of the resources on either side of the constraint, upstream or downstream. All that does is create additional WIP. And then fourth, we want to elevate the constraint. So now that we know how to manage it and we have things flowing through the constraint, at some point in time, because this is likely going to lead to increased demand, we're going to want to know how to elevate the constraint so that we can do more business. It might be even okay to move the constraint from where it's been initially established. The opportunity here is that we can anticipate what we may want to do in that regard. And then the fifth step, and probably the most important if we want to sustain the benefits that we got through the first four, is to not allow inertia to really become the new constraint. We need to establish next level targets. That really becomes the key to continuous improvement, starting the process all over again.
Okay, so thanks, Scott. That's a great overall framework. Now, how is TOC better than other continuous improvement approaches?
I would not say TOC is better. It is different in that it offers a unique focusing aspect. For years, throughout the 80s and 90s, and even into this century, the dominant continuous improvement philosophy was Lean Six Sigma, powering the huge success of the Japanese auto industry, which leveraged the quality teachings of Edwards Deming and Joseph Juran and applied to the Toyota production system. As this image conveys, TOC, Lean, and Six Sigma are complementary rather than competing tools. Lean as the umbrella philosophy of waste reduction, Six Sigma as the means of reducing process variability, and TOC as the focusing element. A study conducted in 2006 indicated that when applied in the proper proportions in any company, they deliver huge dividends.
Thanks, Scott. This chart is really helpful in explaining how these capabilities tie together. Now, how about some success stories? Do you know of any companies that have documented their benefits from the use of TOC?
There are several, but two that come to mind most quickly are Ashley Furniture and Bedford Reinforced Plastics. Ashley has been a TOC champion from the start. Through disciplined application of TOC, the company has reconfigured itself to better serve the needs of its target market more than 20 times. Ashley was an early adopter of TOC as a strategic advantage starting in 1993. They offered 7-day delivery when the industry standard lead time was 6 to 8 weeks. Ashley routinely grew at 40% per year at the expense of its competitors, who were offshoring their production, cutting their product offerings, and in many cases, ceasing to exist.
Okay, now how about Bedford?
Bedford, a much smaller company, but has really figured out how to leverage the ability to fulfill its commitments. Bedford is so confident that its ability to fulfill its delivery promises that it has what I believe is the best guarantee in the business. Bedford also puts its money behind its commitments. If they miss a delivery, they pay the penalty. In this case, you see the first day an order is late, the customer gets a 30% discount on that order. The second day, an additional 20%. And then every day after that, another 10% until the product is free. And they've been honoring this policy for the last 20 years.
Okay, really, really interesting. I guess what strikes me is that Ashley was achieving double-digit growth while other companies were offshoring. Now, Scott, if there was one thing that a company could do right now to benefit from theory of constraints, what would you recommend?
Well, let's start with the first focusing step, identify the constraint. Just draw a simple flow or block diagram of your critical routing from raw material receipt through the production steps to shipping. Then estimate the capacities for each work center. This will serve as the basis of an initial discussion, either via web conference or a site visit with us. The result of this initial mapping and discussion effort will be the foundation for a potential improvement initiative.
Okay, thanks, Scott. Your recommendation and offer sound both doable and practical for those attending today's session. Now, Scott, I've heard you reference DBR as the engine to high on-time delivery. That's a pretty bold statement. Why do you say this?
In our previous session, we discussed the merits of the broader TOC continuous improvement framework. Under the TOC umbrella, there are two key principles that make TOC work: drum buffer rope schedule execution and throughput measures. Today, we'll focus on DBR, and I absolutely do believe DBR is the engine of high on-time delivery. We will explore three components: the root causes of delivery performance, the effect of dependency and variability, and the sales and operations disconnect.
Okay, great setup. Now, Scott, I've seen reports that indicate that the average manufacturer's on-time delivery performance in many cases is barely 80%. Can you take a few minutes to explain why so many companies have such poor delivery performance?
Sure. Let's take a look at the internal supply chain, the four walls of a typical manufacturing company. We buy material, we add value based on our true value proposition, and we ship to our customers on the date we committed. Simple, right? Adding value is how we satisfy our target market customers. Take the market for women's dresses, for example. Each one of these companies sells dresses, but their target market customers are quite different. In the case of the Walmart shopper, tens of millions of them, they are looking for price value. In the case of a dress, a $50 dress. The Nordstrom shopper, tens of thousands of them, if not millions, is buying great service value in the form of selection, return policy, and knowledgeable salespeople. They're looking for a $500 dress. And the Versace shopper, possibly thousands of them, is looking for the unique design and materials value of a look to wear on the red carpet at the Oscars, the $5,000 dress. Different target market customers, different market demographics, different value propositions. Things are now getting a little more complicated. Let's now consider the extended supply chain. And let's further consider our firm is a small player engaged with demanding customers and suppliers. And let's further consider that the supply chain would be several links in length. Things just got a whole lot more difficult. But the challenge of the situation is not yet fully described. In addition to the fundamental market issues companies face, they are also challenged by business systems that assume unlimited material and capacity availability, have no provision for dealing with variability, and lack synchronized information flow. To be honest, Drew, I'm amazed the average on-time delivery performance for any company is even close to 80%. And when it is usually accompanied by high inventories, overtime, and outsourcing costs driving poor operating profit.
Wow, that is a great strategic overview, Scott. A bit complex. So let's see if we can peel back the onion. So in our prior conversations, you have mentioned dependency and variability as facts of life in a manufacturing setting. What exactly do you mean here?
Okay, so here we have a theoretical example of a typical routing. A finished good C made by combining two subassemblies, A and B. As we see, the finished good is created by transforming two raw materials through a repeatable progression of 8 discrete production steps. Not only do these steps have to occur in the order shown, but each step can vary in terms of time it takes, faster or slower than the demonstrated or average time. No operation ever starts or stops when planned, and none of them ever operate at the average speed. In this example, the market demand is 60 units per period. There are 8 steps in this routing through the work centers of varied capacity, ranging from 50 units per period to 120 units per period. I'd like to pose a question to our attendees. What is the throughput of this system? It should be pretty clear that throughput of this system is 50 units per period. The capacity of Work Center 6, the forging operation. Makes sense, right?
So yes, it does. And so what I hear you saying is the forging operation is the constraint at 50 units. So it actually governs the throughput for the entire system.
Correct.
Okay, Scott. So given we have awareness on the constraint, let's touch on how most companies manage capacity. This graphic does a pretty good job of representing how ugly the sales operations disconnect might become. Can you explain for the group what is going on here and why it matters?
Yes, ugly is a good adjective. This image depicts what is current reality for most discrete manufacturers. Here's a representation of the production schedule looks if we were to peer into the typical ERP planning engine to see what is going on in the forging work center that we referenced earlier. I call it the March of the T-Rexes, partly because of the way it looks, but mainly because the thinking causing this is prehistoric. In most manufacturing companies, orders are happily accepted based on the quotation of the firm's standard lead time, say 4 to 6 weeks, or simply saying yes to any requested date to win the business, then throwing the orders over the wall to production without regard for the true capacity of the organization. Now, here you see these green blocks represent essentially work orders that are to be produced in the forging work center if they're going to be delivered on time. In this case, we have orders that to be completed on time when we committed them would have to be processed by 20 machines in this work center, when the true capacity is only 4 machines. Guess what must happen? Orders must be prioritized. But by what means is this accomplished? The most loudly screaming customer, the latest order, the largest order, the most profitable order or customer? This is the scenario on which many companies operate. They are constantly grappling with how to allocate overbooked capacity.
Okay, so again, significant complexity, and you've set up the problem. So how does DBR address the problem?
Okay, so there are essentially 3 components of DBR. The drum is the system's constraint. Let's set the pace of production. It dictates the throughput of the system. It may not actually be a bottleneck, that is a work center that operates at or below the market demand, but it is a capacity constrained resource relative to the resources around it. Regardless of its true nature, it should be considered a flow control point. The next element is the buffer. It is the means by which a system absorbs the typical process variability. Workers not showing up for work, machines going down unexpectedly, bad material, bad weather. and very typically customers changing their mind about quantities and delivery dates. The rope is essentially the communication mechanism for preventing the overcommitment of the drum resource and the synchronization of the material flow from suppliers into the production system through the drum and then on to the customer.
Okay, Scott, so thanks for this setup. So let's move on to application. How does a real company apply the DBR approach?
Okay, so here is a representation of a real ready-to-assemble furniture manufacturer that we worked with several years ago. In this particular case, the material flow is exactly like that of the conceptual model we saw earlier. We have identified the shape operation in red as the constraint. And this company has several target market segments it serves, not just one. We must now protect the shape work center from being starved of good parts to process. We do this by inserting time buffers to protect the drum and also at material receipt, the final assembly leg before shipping, as well as the shipping buffer to ensure on-time delivery of make-to-order product. We are also employing a stock buffer to ensure we have proper finished good levels to serve online customer and distributor demand who expect overnight shipment. Key is the ability to avoid overcommitting the system constraint, like we saw earlier. So the due date quotation process, represented by the rope, is simultaneously testing capacity and material availability. We don't want to overbook our constraint. So now that we have a means by which we can link demand to capacity, we close the communications loop by adding a rope to signal material release. We only want material to flow into the system at the pace of the drum that we have now properly committed.
Okay, great, Scott. Thanks for the walkthrough there. Now, Scott, I understand there are many different flow variations within manufacturing plants. Does this matter when discussing the merits of DBR?
It does, to the extent that everybody thinks they're a little bit different. The production example I use today is referred to as an A plant from a material flow perspective. In an A plant, purchased and manufacturing components are combined at various points along the way to create a finished good. In a V plant, possibly a steel mill, for example, it is the opposite. A single raw material is progressively transformed into a variety of finished goods at every routing step. A T plant, possibly a configure-to-order computer maker like Dell Computer, makes multiple standard components, which are packaged to customer specifications. In an I plant, it is simply a case of transforming a product through several steps in a straight line, no convergence or divergence. All of these material flows, no matter how complex, are characterized by dependency and variability. They have constraints to flow and are supported by DBR to achieve high on-time delivery.
Okay, Scott, so thanks for this overview. So what I hear you saying is that every node, regardless of the plant configuration, can be a constraint, which then impacts the level of material and labor for every other node.
Correct.
Now, if we shift to application, is there one thing that a company can do right now to benefit from the insights you have provided about drum buffer rope? If so, what would you recommend?
Sure. In the last session, we ended with the suggestion to work on identifying the constraint to flow. Now we're at a point where we can talk about how to protect or buffer the constraint against variability. I invite you to connect with me via video conference or possibly a meeting in your plant to develop an initial buffer strategy to improve the flow of your fulfillment mechanism.
Okay, so thanks, Scott. A practical, no-cost offer.
Correct.
Scott, you're an ops leader with specific expertise in theory of constraints and balanced flow manufacturing. Yet you say there is an easy way to peg a company's value proposition. I'm a little skeptical. What do you mean here?
Okay. If a company is not sure about its value proposition, whether it be price, product, or service leadership, a simple way to know is to ask its profitable customers. When companies profile their customers by profitability, this is usually what the data looks like, as you can see in this chart. Typically, 20% of a firm's customers contribute 80% of its profits, which begs the question, why are 20% of our customers willing to pay a premium for our products and services, effectively subsidizing our ability to do business with the other 80%. It is likely the case that the 20%ers are paying a premium for your true value proposition. price, product, or service. This picture suggests that some of the firm's limited expensive capacity is being allocated to marginally profitable or unprofitable customers. The next question is, what can be done about this? Should they just fire the value detractors? Let's come back to this a little bit later.
Okay, Scott, so this makes sense. A significant percentage of customers can be unprofitable, and so in reality, they need to be addressed. In our previous conversations, you've advocated the use of different measures when making manufacturing decisions in relation to these customers. You referenced a lens to view manufacturing decisions different from conventional wisdom. What do you mean here?
That's right, Drew. Traditional cost accounting takes us down one path that causes us to make operational decisions on the basis of gross margin contribution. So here we have a chart showing the classic gross profit analysis of two active products, product A and product B, each having the same standard cost of $5,000, but different selling prices. In this case, product A generates a gross margin of $200, while product B generates a gross margin of a negative $300. In most companies, there would be lively discussion about why are we selling product B at all? But at least there would be a deep dive on the reasons for poor profitability. But for now, let's assume that there's a valid reason for continuing to offer product B, possibly as a loss leader. I'm advocating an alternative approach as a basis for decision-making in addition to standard cost accounting.
Okay, so under standard cost accounting, one product may appear profitable while another may appear unprofitable, but you're suggesting we need to look deeper. Great, so let's explore that further. Can you begin by walking us through the building blocks of your new measures?
Yes. As you can see here, there are basically three building blocks. The first, throughput, T, is essentially the money generated through sales, not production. The way you calculate it essentially would be to take the net sales of the period minus the material purchases at purchase price for the period, minus all totally variable costs, such as commissions or freight. The goal of throughput is to be maximized. This is a growth-oriented measure, and it's something that we would always want to focus on in a TOC environment. The next measure, investment, or I, is the money paid for items intended for sale. So typically this refers to inventory, raw material. But in theory, it could also be the equipment that you use because at some point in time, it could be sold. But the calculation here is I would be the little I for inventory, and the large I or investment would be the capital investment, property, plant, and equipment example. The goal here in most companies would be to minimize the I. The same thing is true for operating expense. Now, operating expense is the money spent to convert I, inventory, into T, sold product. OE is all expenses, including all labor. This is a critical distinction here. The goal would be to maximize T while simultaneously reducing I and OE.
Okay, these are the building blocks. So let's move on to some examples of the measures.
We've all heard about profit, return on investment, and cash flow, but few of us really know how we individually impact them. But if we try to influence T positively, throughput, more sales essentially, we would positively impact ROI, profit, and cash flow. If we drive down investment, primarily inventory, we typically improve ROI and cash flow. And if we reduce operating expenses, we also improve upon profit, ROI, and cash flow.
So we want to increase throughput, decrease investment, and decrease operating expense. And when we do, this opens up a view of different throughput measures we might want to track, such as capital productivity, which is throughput over investment, TI, and employee expense productivity, which is throughput over operating expense, T over OE. The different measures look intriguing. How can we apply these measures to product mix decisions, Scott?
Okay, so let's continue with our evaluation of product A and product B. Now, though, we have a little bit of an additional piece of information. We actually have a constraint that both products go through. Product A takes 1 hour on the constrained resource, and product B takes 7/10 of an hour on the critical resource. So we could do 1,000 units per month of product A and 1,428 units a month of product B. The revenue for each of those production quantities would be $5.2 million for product A and just over 6.7 million for product B. But the material cost, which is variable, would be $1 million for product A, and it would be $1,428,000 for product B. Makes sense. The operating expenses are the same. And again, operating expense includes labor as the most dramatic component. No matter what product I make, the resources are going to remain the same. So $4 million for each product. The interesting part is that when we look at the margin contribution from a throughput measures point of view, product A only contributes about $200,000, where product B would contribute over $1.2 million.
Okay, so the impact considering throughput measures might be significantly different than when we make decisions solely based on GAAP standard accounting. So Scott, would one always prioritize the high throughput products?
Yes, but here is where the notion of high octane comes from. When we discussed in the 5 focusing steps of TOC, we identified the second step as exploit the constraint. As we just demonstrated, the way to fully exploit the constraint is to maximize the flow of products with the highest throughput per constraint time unit. In this case, product B.
Okay, so again, we come back to optimizing against the constraint. And the fact that product B requires 0.7 hours on the constraint versus product A at 1 hour on the constraint can have a significant impact on the decisions we make. That's very powerful. So Scott, are you suggesting that we just cut the customers below the line?
Not at all. In a recent review of a client's customer base, it was determined that the companies in the 3 bars at the far right of this chart represented $1 million in negative gross margin. If all the client did was just raise their prices to 0 gross margin, not get rid of them, but just raise their prices, they would improve the profitability of the company by $1 million. They could also just stop selling to these customers, so in effect, fire them, which would have the same financial impact, but it would also free up constraint capacity for the most profitable customers. A third option would be to survey these customers to see if they could be converted from value detractors to value adders by simply adapting your offering. It's God knows how hard it is to attract new customers. I advocate creating this chart as soon as possible, just to see what is going on and if there is a revenue or profit improvement opportunity that could be initiated immediately.
Okay, so this is helpful. So we do not necessarily want to cut the unprofitable customers. What we want to do is convert them from value detractors to value adders. Easier said than done, but there is a definite call to action here. So Scott, if there was one thing a company could do right now to benefit from throughput measures, what would you recommend?
I would ask you to provide your NAICS code, your industry classification, and revenue range for your business. Then I would create a report showing performance trends of your peer group. Then together, we would discuss appropriate throughput measures you might want to prioritize as you improve your operation.
So Scott, again, great action step.
Okay, everyone, we're coming to the close for our time today. If you have questions, please feel free to reach out to Scott or myself. And if we have your email address, we'd be happy to send you a copy of today's slides. And finally, if you're interested in balanced manufacturing flow for your operations, we'd be happy to engage you in a no-cost consultation to begin scoping the performance improvement savings for your business. Thanks for joining us today. We hope you have a great rest of your day.